Hello everyone, I'm Wang from Zhejiang University. Today I'm going to introduce our research project, MPInspector. This is a joint work with students, professors, and researchers at the University of Virginia, Georgia Tech, and Ant Group. Nowadays, cloud-based IoT platforms are popular. They use messaging protocols to connect IoT devices to the Internet. IoT platform, the device and the user send MP messages to each other through the broker. The messages usually are critical and sensitive, such as the user's sleep routine and the command like open the door. The MQTT workflow shows the client and the broker use connect and connect messages to start a connection. After that, the app subscribes a device topic, then the device publishes a message to the topic, and the app will receive this message. Recently, several MP flaws have been spotted, including DOS, data theft, and command injection. So far, IoT platforms still have limited understanding about the security of MPs. From these security reports, we conclude two threat models, including neighbor scenery and tenant scenery. Considering the threat model and the large amounts of different IoT platforms, the pressing question is how to build a systematic and automatic tool to evaluate the security of IoT MPs. To answer the question, there are two main challenges. First, there are multiple types of MPs, such as MQTT, CLAP, and AMQP. In real world, the MP implementations are customized in terms of message semantics and interaction logic. There is an example of a real published message from Tuya Smart. The parameters topic and the message are customized. As for interaction logic, when two devices connect to the broker with the same client ID, the former device is kicked offline on Google. However, on Bosch, the two devices are both connected. Second, MP workflow is complex, which is stateful with multiple messages. Even worse, the implementations are closed source. For example, Amazon and Azure do not open their source code on the server side. Some works have made great effort to identify MP flaws, but most of them are manual, which requires significant expert effort and is laboring. Previous works have used some clever intuitions on other protocols. However, they mostly focus on the specification rather than the implementation. Or they use fuzzing. Fuzzing is unable to find the logic flaws that do not cause crashes. So there is no good way to systematically evaluate the security of MP implementations. To overcome the two challenges, we propose MPInspector. We follow a property-driven and model-based testing philosophy. First, we model an MP implementation into a state machine. Second, we gather the security properties from the standard MP specification and extend them. Finally, we detect property violations on the state machine by formal verification. As for the desired properties, we consider secrecy and authentication properties. The former is a set of parameters that should be confidential, and the latter is a set of messages that should be authenticated. For the modeling, we model the MP interactions as a state machines. Here is an example. In the state machine, the messages trigger the transition from one state to another. The transition logic is also referred to as interaction logic. Here is a brief overview of our framework. Before formal verification, we apply two automatic modules to construct the state machine. For transition messages, MPInspector extracts their detailed semantics. As some parameter semantics are self-contained in the traffic, we use pattern matching to extract them. For example, the parameter where message is in the JSON format that contains key value pairs. The key username indicates the value's semantics. Some parameter semantics are hidden in the traffic, which is not trivial to extract. For example, the password encrypted by unknown crypto function. We found that the IoT platform document describes the parameter semantics. In such cases, we adopt an NLP-based document analysis. This model mainly consists of traffic and NLP-based semantics extraction. After that, it generates a map to assign the parameters with their semantics. For interaction logic, we apply model learning, which has been proved effective in TLS. Model learning performs membership query and equivalence query to construct a state machine. Queries include inputs and outputs. Specifically, inputs are different message sequences and is sent to the broker. The outputs are the relevant responses. Considering there are multiple parties and multiple types of messages, we extend the adapter to send all types of messages from all involved clients and monitor their responses. Considering of various types of message, the equivalence query needs to send all the permutations of messages, which is of high performance overhead. Thus, we design a customized equivalence algorithm to cut down unnecessary inputs. Another technique challenge is that the existing active model learning may produce uncertain responses because of uncontrolled factor. For example, failing to receive an expected response due to timeout. In such a case, MPInspector may be trapped into an endless learning procedure. To overcome it, MPInspector stops the learning procedure if the same state machine is generated more than once. However, there are some validity predicts that cannot be extracted by model learning. The validity predict describes a constraint that a parameter should satisfy in a transition. For example, the client's password should be validated, or the current delivery ID should be less than the former. To model the predicts, MPInspector sends messages with carefully mutated parameters to the broker and observe if they are accepted or not. After that, the property generation model extends the meta properties. Then the state machine and the security properties are translated into Tamarind code. Finally, MPInspector applies Tamarind Improver to perform formal verification. The final outputs are the violated properties. As for the formal verification, the Tamarind Improver may fail to prove some properties, as some MP implementations have complex state transitions. To overcome it, we design a helping oracle. It is a script that adjusts the order of solving goals during the proof. When we need to analyze a new MP, first, the parameter decoder and the adapter need to be updated to support decode and encode MP messages. Second, the meta properties and the initial state of MP need to be provided. All the above knowledge can be learned from the MP public specification. For evaluation, we utilize MPInspector to explore MQTT, CLAP, and AMQP implementations on 9 leading IoT platforms. For ethics consideration, all the experiments are performed on our own services and devices. MPInspector has identified 252 property violations, leveraging which we further identified 11 kinds of attacks. We present some typical attack workflows under the neighbor scenario and tenant scenario. Also, MPInspector is lightweight. The The average overhead is about 4.5 hours, and MPInspector have 100% precision for property violation detection. Our research further shows that the main root causes of risky MP implementations are as follows. First, the gap between MP implementations and standard specification. Second, the undermined security mechanisms under the resource-constrained IoT context. And third, the lack of careful consideration about device sharing, multi-party involved communications. We are going to design a fine-grained and flexible testing approach and explore automatic meta-property extraction. In conclusion, we propose MPInspector, the first systematic and automatic framework for evaluating the security of MP implementations. We have conducted a large-scale experiment and uncovered 11 kinds of attacks. We have open-sourced our framework. That's all. Thank you. Any question?